So we're going to look at our last type of structure today, metallic structure. Now you'll note you may not have talked much about metallic bonding before now because they're both so tied together. You can't really discuss the bonding in metallic without talking about the structure, so we'll talk a little bit about how the bonding works and then how that affects the physical properties. So our last type of structure is metallic to look at. So in a metal, and this is the tricky bit that some people don't get, if you have a metal, you have millions upon millions of metal elements, atoms in there initially. You don't just have one, even though in the formula we would write just Mg, there's an infinite number of them in there essentially. So when we look at a piece of metal, we are looking at ions held together by strong bonds, again, in a regular structure. So you will have a metallic lattice again. And the bonds are very, very, very strong in a metal. In general, they will have very high melting and boiling points. And they're pretty hard and strong, which is why we make so many things from them. Because you have a strong bond between the two components, the electrostatic attraction. So we tend to have high melting and boiling points, and they tend to be pretty hard and strong. So in a metal, the atoms, when they're initially put together, will lose their outer shell electrons. So if we're looking at a group 1 metal, it will lose its one outer shell electron. If you're looking at group 2, it would lose the 2 outer shell electrons. And those electrons float around between the metal ions as a sea of delocalized electrons. So like we talked about in graphite, those delocalized electrons are able to move around between any of the ions they want. They're not attached to any of the ions anymore. So as metals have lost electrons, they will become positive ions, and we will have the delocalized electrons between us. And this is where our electrostatic attraction for our strong bond comes from. We have the positive ion and the negative sea of electrons, so the attraction between them is what gives us the very, very strong bonds. So how does this affect our structure? Our structure is going to be our lattice, it's going to be nice, neat rows. What does that do for our properties? So let's go have a little look. So here we have our little model of a metallic lattice with our black little spheres being our positive ions, and our little white nodules are our sea of delocalized electrons. So as you can see, it's a nice neat lattice. We've got that repeating unit of the positive ions. That means it's quite easy to shape a metal, the property of malleability, because the sea of delocalized electrons are always moving. So if we try to bend this, if I try to push, the whole row will slide past one another, okay? They will move and slide past one another. There's nothing stopping them from sliding. You're not going to break the bond like you would in a covalent, and you're not breaking the bonds in the ionic. Obviously, if you slide them, the positives and negatives line up and they snap apart, which is why they're so brittle. Whereas the metals, the sea of delocalized electrons just moves with the sliding, so it's very easy to shape them. The other advantage our metal has is obviously the delocalized electrons are not held in place, they're moving around, so they can conduct heat and electricity, and this is why metals are such good conductors of electricity. That sea of electrons can move in between all the positive ions, carrying the current, carrying the charge, but without destroying the structure, because more delocalized electrons can move in and replace them as they move. So it's a very good conductor of electricity. So as you can see from the little model, the huge numbers of delocalized electrons make them good conductors of electricity and heat because they are constantly moving around, they can carry the current. And the regular structure means the layers of atoms slide over each other fairly easily without breaking the bonds, although definitely not as easily as graphite. Graphite's layers definitely slide much more easily. And so they are malleable, they bend rather than snap. And as I talked about, because these are positive and they're being pushed along, they won't start repelling one another because of the sea of delocalized electron, whereas ionic would be swapping from negative and positive, and they'd end up lining up and repelling one another. So in summary for our metallics, they are strong, malleable solids, they don't dissolve, and we would talk about having positive ions and delocalized electrons making up our structure. And our properties, we were most likely to have a high melting point and boiling point, and then being hard and strong because there are strong bonds between the ions and the delocalized electrons. They are malleable because they have that lattice, that regular structure, and the layers can slide over one another pretty easily. And they conduct electricity and heat very, very well because the delocalized electrons between the ions can move around very easily. Now, it is worth noting with this regular structure and layers that slide, that if you have a mixture of metals or an alloy, because the ions are slightly different sizes, that sliding gets much, much more difficult, which will make them harder and less malleable as well. So hopefully that is all of our structures, and we can go on to talking about how to use the language correctly.